So a couple of announcements. These came up after the break in the other class, so I want to cover them now. I might push, so you have homework one. Homework one looks long, and it's a little shorter than last year, and I want to kind of go through. If I had time, I'd go through it, but we'll go through a little bit of it. Problem one, super keys and candidate keys should take you about 10 minutes. Problem two, which is a schema problem, looks very complicated. It's meant to be very tedious, so you pick the right data types. So it's not meant to trick you. Every word that's in there is usually in there to hint to you what type of data type you should use. With that said, a question came up about whether you should use MySQL types or SQL standard types. It's up to you. My motive there was to use MySQL types. Those are concrete types. But you can use SQL standard types if they exist in MySQL as well. They do typically. So somebody who's asking, should I use medium int? Should I use int? If you're going to use a standard, just make a note in a comment that you're using the standard data types. That way we don't mark you off. We know, okay, they're using the standard. They're not going to using tiny, medium, humongous, giant, big, and all that fun stuff. Speaking of comments. So I've looked at some of the submissions. So some of you are doing the work on Gradescope and saving it. That's fine. I mean, it's a good place to save it. It's secure. There's a couple things that are happening though. One, I've looked at some of the saved work and it won't compile or it won't run in MySQL. And what we're gonna do is we're on the querying part, we're going to just run your query and then check it manually if we need to. So if you've written English in your query, you need to change that. You need to make it into a comment. So remember, a comment starts with two dashes, like that, and you want to, for however long your English is, just do dash dash, maybe 10 words. Hit enter, dash dash to create another comment to continue your work, basically. If we cannot run it, it'll lose points because it takes too much time to review. So make sure you comment if you write anything other than your query. Also, another thing that's happening is when you're saving your work, for some people, it's submitting it. That's okay. It's not ideal. We're going to grade the most recent submission. So if you've submitted 5 million times, we're only going to grade the most recent one. But it's very messy, and we have had issues where we've accidentally graded the wrong version. So it's better if you either do your work in another editor and then submit it in Gradescope when you're done, or just minimize how many times you're submitting. I'm going to talk to Song and see if there's a way that we can have you submit one submission. You can edit it, but it's one submission. This whole submission thing is a little bit weird. The due date, I'm thinking about possibly pushing the due date to Thursday because we have office hours on Thursday. If I don't do that, I'm a little bit hesitant to move it, but if I don't move it, then I'll move my office hours to Wednesday. I'll decide that by tomorrow. There also seems to be, at least with one student, an issue with copy and paste. And the reason I mention this is because I've seen it happen in my other class. For some reason, people can't copy and paste into Gradescope. I don't know why. I don't know if this is an anti-plagiarism thing or what, but it seems to only affect Windows. So I've asked Song, or I'm going to ask Song to look into that. I told the student, post on CampusWire to everyone, thumbs up it, comment on it if you're having the same problem, and then Song can look into it. All right, that's all out of the way now. We can now move on to this topic. My head is this is out of the 5 lectures, this is probably the most difficult one. This is pretty hairy. So if you follow along excellently and are bored or understand everything, you're in excellent shape not only for this class, but for interviews and moving on. If you're struggling a little bit, well, you're in the right place, you're learning. I mean, it's intense to get through this in 3 hours. If you're completely lost though, you need to start coming to office hours. I hope nobody's in that boat. But sometimes people are. So let's go ahead and get started. Last time we didn't talk about modifying data, so we're gonna start there. I need more space. Oh, there we go. That's all I need. So last time, we've talked about creating tables and altering schemas of tables, as well as dropping deleting, and truncating tables when you want to remove data from a table. We also talked about retrieving data from a single table using a simple select from, where, group by having, and whatnot. Now we're going to talk about adding new rows to tables, as well as modifying values in existing rows. Then we'll talk about joins and subqueries. Now, in your career, it's probably going to be pretty rare, unless you're at a startup where you're a data engineer. It's pretty rare, but you're going to actually modify or delete data in a database. Typically, if a data is given to you, somebody's loaded data into the database, a data engineer or the product itself is loading data in there. And typically, you're not touching that data, you're only reading that data. If you're at a startup, though, or you're a data engineer, you might touch this data. And also, while you're practicing for this class, you may want to create some fake data, toy data sets that you can play with. And in order to do that, you need to know how to create a table, insert rows into a table, update values in a row, and also delete rows from that table. So helping you learn, you learning yourself in addition to lecture is extremely important. And doing this stuff can help you do that. But typically you're not going to see inserts and updates a whole lot. So we had this Bruin-based relation last time, I think. And we're going to change a couple things in it. We're going to call it midterm scores now. And it contains information about students, popular Bruins, UID, last first name, middle initial, midterm score, their major, their level, and their career, undergrad or grad. And if you want to follow along, I have created this table in your database, the read-only database. You can copy that table into your own database if you want to follow along. And how you do that is using this query if it's on the screen. This is actually a fairly important query because there's going to be times where you need to make copies of stuff at work and whatnot. And so we do create table. Well, the first thing you're going to do is use whatever your database name is, which is your username. Then you're going to create a table called midterm scores in your database and then we specify a select query that pulls all the data out of another database and puts it into a table in your database. Now, I know I've talked excessively about don't use select star. For analytic queries, which is most of what you're writing, you don't want to write select star because for various reasons. This is more of an operational query. We don't care. We want to just select everything and put it into this new table. Nobody needs to read the query once we're done with it, only us. The thing .midterm scores, because I'm in my own username database and I want to pull data from another database, I need to specify what that database is. So I do select star from MGMT MSA 402 .midterm scores, table within a database. So if you do that, hopefully through all of my talking, you are able to do that. For those who want to, you don't have to, you can follow along without. Now there's two ways to insert new rows into a table. Two different syntaxes. The first is where we fully specify the row and all the values for all of the columns. This is very readable and it makes it reading the query very easily because we know what each value represents. The order of the values matches the schema. So matches schema. If my schema is column 1, column 2, up to column n, value 1 must be the value for column 1. And value n must be the value for the last column. I cannot leave anything out. All of the columns are fully specified, so it's easy to read. Now, I probably should have done this instead. We can get rid of this semicolon. Typically, you want to insert multiple rows at a time. So instead of a semicolon, we can put a comma instead, and then we can add another row. Value A, value B, all the way up to value n. And then so on and so forth. So you can add many, many rows. Now, I've posted the queries for this lecture, as I always do on Brew and Learn. And you can see that I do this. I create a table, and then I call an insert with a bunch of rows, insert rows into that table. If you read that code, which I encourage you to do, it'll teach you basically how to create toy data sets. So really, once you understand these concepts and know how to create your own data, you can actually answer a lot of your own questions. You can always ask me, of course, but sometimes when you're studying, you come up with a question, it's 4 a.m, although I'm probably awake. You can probably answer the question yourself by writing a query against a toy data set. So that's one way to insert values into it or rows into a table. The other way is a little bit less readable, but it's more flexible for the user. So what I can do is I specify essentially a mini schema, what I call a mini schema. This basically says the first value in each row corresponds to column 1, whatever column 1 is. It may be the first column in the schema, it may be the fifth, it doesn't matter, and so on and so forth. I specify the order of the columns that I want to insert values into, and as long as I'm consistent, I can reorder columns, so I don't have to enter values in the order that the columns appear in the schema. I can even leave columns out. If a column is nullable, meaning it accepts a null value, or if it has a default, like a timestamp, maybe current timestamp is the default value, you can leave that column out and not insert a value in it, and the database will automatically insert the default value for you. So 2 things this allows you to do: reorder, insert in a different order, I should say. Insert values in a different order. And 2, it allows you to leave out columns. Rely on defaults for omitted columns. So this can be really useful. It's very flexible, but it's not as readable. Now I need to figure out, okay, what did you do with the order? Why did you order the columns in this certain way? Now note that even though you specify the columns in a different order, they all get put into the right place. So in the schema, if you have columns A, B, C, D, E, but in here I insert into columns D, E, A, C, and B, it'll be stored as column A, B, C, D, E. That's kind of cool, but it's not as readable. Either one's valid though for this class. Just know though that you need to have if you leave out a column, it needs to be null or nullable, not null, but nullable, and or needs to have a default value. Otherwise, it's not syntactically correct. So are there any questions about insert? So here's an example. Let's say I have a midterm scores table. I have a new student that just took the exam. They took it late or something. Now I want to add a record for them. This student's name is Edward F. Codd, who is one of the grandfathers of relational, or maybe the father of relational database theory. He and date. In my opinion, there's a little bit of a rivalry between the two, but they have some different opinions about the theory. Anyway, in the first case, I specify all the values for every column. So I specify his user, his UID, his last name, first, middle name, score, major, level, and career. So fully specified row according to the schema. Very easy to read. I know which column is what. The other way I could do this is, let's say I have a default. Here I don't have a default. I can't remember if last lecture I created one. Oh, the middle name, the middle initial. So let's do that. Here, let's get rid of middle initial. So here I've changed the order of a couple of the columns. I don't remember which. It's one of the last 4, level, major, midterm, and career, are switched from the schema. So here I've reordered the columns. I'm also not going to give him a middle initial. I'm just going to rely on the database, is whatever the database default is. The default could be an empty string, or it could just be null. It doesn't matter. But the database will not complain if I use the second insert without a middle initial. So any questions on insert? All right. Modifying rows, again, something you really probably shouldn't do, but if we need to, we'll teach you how to do it. We use the update statement for that. It's a very simple syntax. It's simply update the name of the table, and then there's a set clause. Set whatever the name of the column is equal to some new value, or an expression. And there should be a where. Now, on your database, we've added a lot of restrictions. One of the restrictions, I think, is that if you do an update, the update has to have a where, or you have to do the set on the key. The reason for this is that a common mistake is for people to write an update against an entire table and basically change the entire table when they really only intended to change one value in the table. Now, that doesn't really matter for your database because it's your database as opposed to the class database. But you might run into an error. You might see that error. So let's see some examples of this. Let's say on the midterm. The highest score is 98, and I want the highest score to be 100. So I add 2 points to everybody's score. Now I'm sick of this color, so let's switch to this one. How would I do that using an update statement? So I'd start with update midterm scores. Then what? Set. Good. I'll give this next one to you because the schema is a few slides back. Midterm equals what? Midterm plus 2. Great. So this is an expression, not a value. Do I need anything else? Nope, this is a global update. I'm updating everybody's score and adding 2. Now, even in college, some students get a 0 on a midterm because they don't put their name on their paper. Happens at least once every quarter. And so Johnny Appleseed comes crying, tears running down his face, snot going everywhere, just a complete mess. I got a 0 on my midterm, but he really got an 81. So we're gonna update his score. He really should get a 0 because who still does this after 3rd grade? So we're gonna update his score to an 81. How do we do that? Well, we write an update statement. So update midterm scores. Then what? Set midterm. Is it midterm scores or? The column is midterm. The table is called midterm scores, but the column is called midterm. Yes, so midterm equals 81. And? Great. Where UID, is equal to 0, 0, 1, 1, 2, 2, 3, 3, 4. Great. Now he's happy. Then he starts complaining because an 81 wasn't high enough. Anyway. So are there any questions? Is there anything else here? Are there any questions on update? Insert or update. Now we've seen an example of a more complicated, no we didn't. Getting ahead of myself. There is I don't think I wrote this as an exercise, but there's another more complicated thing that we can do. Let's say I don't know, there's a maximum on the midterm. I don't know what that maximum is or who got it. I need to compute it. I can write an update statement to do that. But I have to do something else. I can't just do set midterm equals midterm plus something. I have to compute what that delta is. And I can do that in something called a subquery. So we'll learn how to do that later in this class, and it may come back, so you may want to remember that exercise. So now we're going to, so as I mentioned at the beginning of the quarter, instead of spending the first 2 lectures like 6 hours talking about relational algebra syntax, we're going to learn it by osmosis, and we're going to learn it as we go. And I think it blossomed for last lecture about the importance of relational algebra and how much it could simplify your life once you understand it. Once we go through relational algebra for joins, then we'll talk about how to extend it to SQL, and then we'll move on. So the first concept that we're going to talk, or the first operator we're going to talk about here is the Cartesian product. Now, a lot of you are math majors but may not remember what the Cartesian product is, and many of you were not math majors and don't know what it is. So we'll talk about it now. Basically, all it is all pairs. So if I have 2 relations, it's all pairs of tuples between the 2 relations. What on earth does that mean? Let's say I have 2 relations here. I have R equals, has 2 attributes, A and B, and I have alpha, beta, gamma, and I have S. S is going to have attributes C and D, alpha, gamma, delta, eta. And the Cartesian product works as follows. I look at the first tuple in R, which is alpha, beta, and I pair it with every tuple in S. So I get alpha, beta, alpha, gamma. I get alpha, beta, delta, eta. And if I could change the colors here, I get beta, gamma, alpha, gamma, and beta, gamma, delta, eta. So all pairs. And now I feel like I'm pledging a fraternity or something. It's a little crazy. So what does my output look like? I'm going to have A, B, C, D. This is R cross S. And using the proper colors here, because that's important, we're going to have alpha, beta, alpha, gamma, alpha, beta, delta, eta, and finally, beta, gamma, delta, eta. Oh well, let's be clear. I did that in the wrong order. Alpha, gamma, right, beta, gamma, delta, eta. Exciting, huh? So that is the Cartesian product between two relations. Now, I haven't really used Greek letters a lot in this class because I try to be more practical than theoretical. But it's the easiest way to explain this concept. Now, why on earth would we ever want to do this? Well, really, in implementation, I'll leave this up here for a moment in case you're copying it down. So we really don't ever want to do this under the hood. This is very, very slow. It uses a lot of RAM. When you exhaust RAM, stuff ends up swapping back and forth between RAM and the disk. This is extremely slow because you're constantly swapping back and forth. Even on SSDs, it's very slow. And it takes forever. So when I crashed the database at the startup that I worked at, my first internship ever, this is what I did. I didn't write a proper join condition. I basically ended up writing a Cartesian product, 1 billion times 1 billion rows. Ugh. So we want to really avoid that. But we use it to talk about the join and inspire how we talk about the join. Some of you may already know what a join is or can kind of infer what it means. But if you can't, which I really can't, it's hard to describe without talking about the theory behind this, you need something simpler. And the simpler way to motivate a join is basically creating a Cartesian product, matching every tuple against every other tuple in the two relations, and then filtering according to some join condition. Once we understand that the Cartesian product is the basic operation behind a join, it makes more sense. And we can go back, no matter how complicated the join is or whatnot, we can go back to basic principles and solve the problem. Otherwise, it's more difficult to do that. So I already talked about the slide. Basically, we never really want to write a Cartesian product, but it does happen if we don't write the proper join condition. And we use it to motivate the concept of a join. Now, what is a join? We perform a join when we have two relations that represent two very different things, but we somehow need information from both of them. For some particular business context, we need access to both of them. Maybe for a report, maybe it's to do some analysis on something that we're studying. But even though these two relations are very distinct and have their own needs and issues, they're related somehow. So the result of joining these two relations is yet another relation. But when you write a join, typically it's a result set. So it's not materialized back to the database. It's just exported into the result set. So what are some examples of tables that we can join? We've talked endlessly about the YouTube video and comment table. We'll call this one R and this one S. This first one represents videos. The second one represents comments. And we knew that these two tables were linked somehow. They were linked by this attribute video ID. So R, which is video, videos have very specific attributes that comments don't have, and comments have very specific attributes that videos don't have. But they are still related, and we may need to study them together. And when we need that, we join the two tables together. Now, we also talked about the fact that video ID is a foreign key into YouTube video. Now, yes, that's true, but that's for referential integrity. If I have a comment in the comments table, it better refer to a video in the videos table. Also, if I have a video in the videos table and I delete it, what happens to the comments associated with that video? Both of those points are referential integrity. Foreign keys are not used for joins. You can use them to join two tables together, but that's not their purpose. Their main purpose is referential integrity. But this is also a join key. So it's a foreign key and it's a join key. A join key is just an attribute or a set of attributes, columns, that we can use to join two tables together. There are no restrictions on what we can use as a join key. It doesn't have to be unique. It doesn't have to be a foreign key. We can pick anything to be the join key. Okay. So if we join these two tables together, now you're noticing I'm not writing any notation yet. We'll get there. I end up with the following. It doesn't fit on the slide. So we have 4 rows. And the first 5 attributes are here. The last 2 attributes are here. In your mind, take these 2 and add them here, and you get the joined result. A very, very basic joined result. Now in the original table, here, we've lost a couple of videos. We have this one represented in both tables, so we keep it. We also have this one represented in both tables, so we keep it. But there's 2 other videos here that don't have any comments. So when we join the 2 tables together, we lose those videos because there's no comments with them. Are there any questions so far? Yeah.
So the join key is supposed to be based on some attribute that is common in both of the tables?
So the question is the join key supposed to involve an attribute that's the same in both tables, basically? Depends on what we mean by the same. They don't have to have the same name, but they have to represent the same business quantity, the same context. Yeah, we're actually getting to something that's going to exploit that in a moment, so I'm glad you asked. Any other questions? Yeah.
So you explained that the foreign keys for the referential integrity?
Yes.
What does that mean?
Referential integrity means that if I have a table that relies on another table, certain rows have to exist in both tables. So if I have a comment in a comment table, that comment has to be related to a video somehow. It doesn't make sense to have a comment that's on a video that doesn't exist. It might, but right now it doesn't. It also means, though, that if I have a video in the video table and I have comments associated with it, I need to maintain the link between those 2. If I delete a video, what happens to the comments? A couple of things, and I have to specify what happens. One is that I delete all the comments associated with that video. The comments no longer are attached to a video, just get rid of them. Or the database can give me an error. You're trying to delete a video with this ID, but you have comments associated with this video. You're going to orphan these 2 data points if you do that. Do you want to enforce it? You can, and then you may end up with dangling comments, which is sometimes valid, or you may end up deleting comments, or you just don't do anything. There's data relying on that video, so we just keep all the data. So referential integrity is when across 2 tables, we have rows that are linked and must be in both tables. Or must exist in one of the tables. So any other questions on a join key? Okay. The word key is overloaded in databases, especially in my other class, but as well as in this class. A join key has nothing to do with uniqueness. It has nothing to do with referential integrity. It has nothing to do with not null. It's just an attribute that you use to join 2 tables together. There's also index keys. How is the data sorted? That may or may not be unique. We've talked about primary, candidate, foreign, and super keys as well. There's lots and lots of keys. And not enough locks. So one thing that we're going to talk about in lecture 5 is normalization. So we want to separate concerns when we have a database. Each table needs to represent a distinct object that has distinct attributes and distinct characteristics about it. We don't want to have a table that contains a mixed match of different things. So we have a video table and we have a comments table. In a business setting, we do need to have both at times. But to do that, we just join the 2 tables together. We don't store that result, though, in the database. That's called denormalized. It's nasty in a theoretical sense. It means there's a lot of duplication and a lot of redundant data if we have a denormalized table. So we don't want to have to duplicate a bunch of data. If we did, what we would have is for every comment, we would have copies of the video ID, the video name, the channel ID, et cetera, et cetera. That's a lot of wasted space. So instead what we do is we just keep them separate and we join them when we need them. This process, though, of taking a nasty table that mixes concerns and separating them out is called normalization. And it's pretty important to know how to normalize a schema. So we'll talk about that at a later date. Right, so we join them when we need them. To put a little bit of a fly in the new Chardonnay here, we sometimes do want to have denormalized tables, especially in data warehouses. So in a data warehouse, we have a business case, and we are always going to query against that business case. So we create a denormalized table. We join two tables together, and we store them in the schema. Now, to answer questions about a particular business case, I just execute against that denormalized table instead of having to execute joins constantly, because joins can be inefficient and they take time. So in a data warehouse, it may make sense to keep tables denormalized and mix concerns together so that we can query them much quicker. And again, we'll talk about that in lecture 5. But we're not there yet. We're talking about having tables that are normalized that we join together. Now, I also mentioned that all database systems implement what's called CRUD, create, read, update, and delete. And one thing that makes the relational model special is that we also have a join operator. So CRUD plus J or CRUD J. I made that up, it's not theory, but we do add a join operator in there. Any questions so far about motivated and join? All right. Natural join, so getting back into relational algebra. The simplest join that we can do in the relational algebra is called the natural join. It uses a little bow tie. Maybe one day I'll wear a bow tie to class when I cover this topic. No, I won't. With a natural join, the database takes the two tables, looks at whether or not there's any overlap in the names of the columns. So getting to your question, Hamza's question, if the two tables have one or more columns names in common, it's going to use those columns as the join key. It could be one column, it could be multiple columns. As long as the names are the same, the database automatically picks those columns as the join key, and you don't need to specify it. So we don't do this in SQL, but in the relational algebra, this is the type of join they introduce. So down here, we have the set theory notation, if you're interested, of what the natural join does. And down here, we have the relational algebra way of defining a join. First, we take the Cartesian product of R cross S. This is all pairs of tuples. And then we filter those tuples according to the natural join condition, which is simply that all of the columns have common names between the two relations. The values must be equal between them. We simply check for in R if we have a particular column and a value in that column. We check in S if on that same column we have a value that matches that column and that value in R. If we do, we output that row to the output. If we cannot find a match, then we just strike it out. We don't report that row. And we'll see examples of this in a minute, which makes it a lot clearer. So this filters the join condition, which is picked by the database. Finally, that nasty pi R union S just means we remove duplicates. It means that, to be more precise, it means we take the union of the columns of both relations. So we're going to get a full set. So if I have columns A, B, C in R and columns C, D, E in S, my result is going to contain columns A, B, C, D, E. So let's formalize this. I have a table here that contains information about instructors, just an ID and a name, and the classes they teach. So IN's ID in teaches refers to an instructor, and then the second column is just the class that they teach. So the join key here, I note that I have IN's ID in instructor and IN's ID in teaches. The natural join, the DB picks IN's ID as the join key. And it's going to look at the tables. Okay, good, I might move this note. I'll just draw over it, I guess. So what do we do here? We're going to look, first let's look at Smallberg here, who has an ID of 1. We now look in teaches, and because IN's ID is the join key, we're going to look in teaches and see if we can find another IN's ID of 1. And we see that we have 2 of them. CS31 and CS32. Those match, so in the natural join, I'm going to get back his name and CS31 and 32. Likewise, with Riemann, we have only one match for ins ID2. So that's the only row we're going to get back on the natural join is Riemann and CS33. Eggert, though, has 3 classes here. There's 3 ins IDs of 3 and teaches. So we're going to get 3 rows in the natural join. So these two, Smallberg and Eggert, students love seeing their names up here. They're kind of like folk legends in the department at this point. You basically cannot complete a CS degree without taking a class with one of them. So Smallberg teaches the lower division classes. Eggert is particularly interesting. He's very challenging, a really great professor. He also, there is this database in Linux that indexes all the time zones in the world and the offsets. It also indexes the day that daylight saving time starts and ends, if applicable for the time zone. He manages that database. So that's kind of a big deal at UCLA. And we are the birthplace of the internet as well. So we got some great people who are working on that. I'm glad he's doing that and not me, because it sounds awfully boring to have to index that information. And then so on and so forth. Obviously, we're going to match 4 to 4, 5 to 5, and so on and so forth. I'm also going to add a 12 here. I know 11's missing. It doesn't matter. It's just another ID. And we see that there's no matching 12 in teaches. So this row just goes away. It doesn't appear in the output for the natural join. So when we do the natural join between these two, we get back 3 columns. We get back ins ID, course, and name. But I don't want all 3 of these columns. So what do I do if I only want course and name? I just project out course and name. Now what I do want to say about this first one here is that in the natural join, you get back 1 copy of the key. Exactly 1 copy of it. That's not always true that's not true in the other joins. So you always get back 1 copy of the key. One copy of join key. So as you can see, I have 12 here. Whoops, no, he's not in the output at all. He or she is not in the output at all. Okay, whoops. So the natural join automatically picks the join key. That might sound good, but it's very dangerous. We always compare tuples based on equality. So we compare keys, values of keys, based on equality in the natural join. At least this kind of natural join. Technically, a natural join could be any kind of join. But here we're going to call it an equijoin, an inner equijoin. Now, usually, actually, in almost like every case, I don't want to say every case, just in case, we want to control the join key ourselves. And you're expected to control the join key yourselves in this class. When we specify the join key ourselves, the join condition, key or condition, is called theta, and that join is called a theta join. It's no longer a natural join. And it looks like this. It looks very similar to the natural join, except I have a theta here. And the theta is a condition. It's the join condition. First thing I do is I compute the Cartesian product, all pairs of tuples in R1 and R2. And then filter or select the selection operator using the join predicate, the join condition. Now, I need to ask you a question. This selection operator, sigma, is this the same? Is it analogous to a SQL select? Who says yes? And be confident in your answer. Who says yes? Okay, good. I'm glad you put your hand up again. Okay, a couple people. Who says no? And 80%. Okay, let's do this again. I want at least half participating. Who says sigma is a SQL select? It's okay to be wrong. Who says yes? Okay, cool. Who says no? It's about an equal amount. The answer is no. It depends how I word the question, though. So on an exam, sometimes I'll say, choose the true or false. Sigma is equivalent to SQL select. Is there a better option for that true and false question? Yes. It's equivalent. It's more closely equivalent to a where. There is no other way to represent a where in relational algebra other than this guy. So it's closer to a where. Now, some of you who answered yes may be thinking, well, yes, it's a select star from where. That is true, but it's the where that is really important there. What is more closely related to the SQL select? Which operator? Which one? This is important. We've learned sigma, we've learned x, which one? Pi, yes. Pi is closer to a select. It's actually a select distinct. So oftentimes on a multiple choice question, I'm not saying I would do this, but I might say choose the best answer, not the precisely correct answer, the best one. Sigma is most closely related to A, select, B, where, C, join, and D, something that has nothing to do with SQL. And you should answer, it's mostly closely related to the where. Okay, cool. So the answer to that, true and false, is false. Anyway, back to joins. This select operator is not a select in SQL, it's more like a where. So we're going to filter on a where, or in the join cases an on, a particular join condition. This is called theta. So we can represent the previous natural join as a theta join as follows. We take instructor, bow tie, and in the subscript we put the join condition. Instructor dot ins ID equals teaches dot ins ID. And the other part of the join is, well, teaches. This guy here is theta. Now, why do I use the alias instructor and teaches? Because I have a name clash. I have ins ID in both tables. I'm specifying the join condition explicitly. I have to then list the name of each relation, or an alias, which we'll talk about in a moment. So are there any questions on this theta join? Now 410, so 85, so that's 510. So by 535, I need to remember those times. We'll take a break at that time. Hopefully we don't need one yet, but I promise you will. So again, theta join, two steps. Even with the natural join, there's two steps. First, Cartesian product, then we filter out tuples that don't match on the join condition. So we get this theorem here, that R bow tie S is equal to sigma sub theta of R times S. Now, there's one other operator we need to learn before we move on to SQL, and that's the rename operator. This one doesn't have a very standard definition. You'll see it in a variety of different places. It's the row operator. This first one, the sub S, means that we're going to rename R to S. Now, R could be a relation, or it could be a really complicated expression. Sometimes you need to take the result of a very complicated expression and use it somewhere else and filter on it. So you rename it, you call it foo. And then outside that complicated expression, you refer to foo in order to compare the result of that complex expression to some value or something. Now, this is important, this special case down here. When we take the Cartesian product of a relation with itself, we cannot use R cross R or L cross L. We have to rename one of them. The reason is going to become clear when we talk about joins in more detail. Basically, it becomes very ambiguous. What is R? If I say R.ID, which R am I talking about? So because of that, I have to rename one of them. You can also use the projection operator, remember, to rename things as well, if you're renaming an attribute rather than something else. So in SQL, for those of you who have played with it, what is the approximate equivalent of the row operator? As. Great. Oh, and this one's B to A. All right. Okay, now we're going to move to SQL. But are there any questions about the relational algebra? Cool. So again, we use a join when we have two different tables that have different use cases, and if we somehow have some business context where we need both of them together in order to create a report or to study something. That process is called a join, as we know. But all the ones that we're going to talk about are theta joins. So, an SQL query, I can tell it's SQL because it says an instead of a SQL query. An SQL query walks into a bar and sees two tables. He walks up to them and says, "Can I join you?" Ah, some engineering humor. Now, we talked about the natural join, and we're going to forget about it now. We also talked about theta joins, which we're going to use through the rest of this class. It is possible to do a natural join in SQL. I'm not going to teach you how, because you should never do it. And I'll explain why in a minute. You always, always, always must explicitly specify the join condition. So never, ever, ever, ever use a natural join in SQL. You will lose 90% of the points for any problem involving a join if you use a natural join. Always theta only. So if that's not clear enough, I have this, excuse me. I have this graphic for you instead, as I nearly choked to death. So I'll mention it once or twice more this lecture, and then it'll disappear for a while. So why are we also against natural join? And it's not just me, it's the field in general. When you're writing a query that uses natural join, it's not obvious what the hell you're doing. We don't know what the join key is because the database is picking it itself. In order to understand what a natural join is doing, it means you need to be intimately familiar with the schema of the two tables that you're trying to join. Now, maybe you're going to try to do this as some job security, but it ain't going to work. People are going to see right through it. The column names can change. The column types can change. Oh, and did I mention that you should never change the schema? Well, here's one reason why. Though still you should never use natural join. If you change your schema or change your code, you're going to have to hunt down every natural join and change it. We cannot maintain code that way. So just do not use natural join. If you write a natural join between two relations that don't have any common attributes, you get a cross join or a Cartesian product. Now you've crashed the server. So don't do natural join. So instead, we'll talk about the first most basic type of join in SQL, which is the inner join. In particular, the inner equijoin. So we're going to introduce this concept of the theta join using the inner equijoin, which is the simplest. So I have two tables, instructor and offering, and I'm going to join these two tables together. Now, what is the output going to look like? If I do R join S, I'm going to get back the following columns. I'm going to get back ins ID. I'm going to get back instructor name. I'm going to get back ins ID again for the right-hand side. Let me get rid of that. Ins ID again. And course name. Now, depending on the database, you may just get two duplicate columns called ins ID. You should, though, at least in Postgres, the one I'm more familiar with, but MySQL, I believe, works the same way. You're going to get the name of the relation, so instructor.insID and offering.insID. So an inner equijoin, when you join two tables together that have a common attribute, you're going to get back two copies of the join key. Even if the join key doesn't have the same name, you're going to get back two copies. So they'll have different names, but it's basically two of the same column. So you're going to have to project one of them out if you want to keep only one copy. Or just don't project anything if you don't want the ID at all. So we'll call this L and this R. Let's say down here, again, I have another professor, Smith. Same thing, if I join these two tables together, Smith goes away because I do not have a match on the join key. So I should have done that here. I did it earlier, but the same thing happens here. We join on equality. So we look at 1 equals 1 ins ID and instructor equals 1. We look on the right-hand side offering for another 1. And if we find it, we join those records together. Now here I'm going to get two copies or 2 rows for Smallberg, 3 rows for Egger, and what was funny is the quarter that created this example, I had a student that had all three of those classes with him. He's very hard, plus my class. And that just sounds like not a fun time. I hope they survived. But then I also joined these other ones as well. So Reinman, for example, will be joined to CS33 and so on and so forth. But poor Smith, nothing to join with because he or she is not teaching any classes that quarter. So we've shown how to do this with the relational algebra. We know how to do it in a little picture. How do we write it in SQL? Well, we do the following. Now I'll show you a strategy on how to write these as it becomes more complicated. But for now, it's a little bit more straightforward. I have two tables that I'm joining. One is going to be the from, one is going to be the join. So here's my from and my join. Now the word inner here is optional. It should be inherent to the database what type of join you're doing. In some cases you have to specify it, but for an inner join, it should be obvious based on the join condition to the database. But you may want to get in the habit of putting inner there for your own learning. Then I specify my join condition. I have ins ID in both tables, so I have to use the alias, the table name as the alias. And then finally, I select instructor name and course name. No aliases here because there's no name clash. Instructor name is only in one table, course name is only in one table. Now suppose I select instructor ID also. What do I have to do? Yeah, I gotta specify which side I wanna take. Does it matter here which side I take?
No.
It doesn't, because I'm doing an inner equijoin. In other joins, it will matter, and we'll see that in a moment. But here it could be instructor dot ins ID or offering dot ins ID. Either is equally valid and both will work. They're the same. Okay. Any questions on how to write an inner join or an inner equijoin? I'll define what equi means in a moment in case you're wondering. Okay. Here's the result. This is a Postgres type output. MySQL looks the same except there's a border around. It doesn't matter. Anyway, you see that Smith is missing. So I only keep records that have matches on the join key in both tables. If I can't find a match, I delete that concatenation of the two records. Now, if we want to be real clear, we can put aliases everywhere. And this isn't a bad idea. Now it's crystal clear where everything comes from, even though it's not needed. I sometimes do this. I just think this way. Here, I give instructor a short name called I, and I join it to course, should be offering, but course C, and I call course C. I give it a name. These are called table aliases. And remember that table aliases are defined in the from and the join, which are the first two operations that are executed in the query plan. So I can access those table aliases anywhere in the query. I can use it in my on, I can use it anywhere else. So instead of having to write instructor and course everywhere, I just write I dot and C dot everywhere. Now, these are also table aliases, but these guys here are column aliases. Now, some of you, you can also put as here as well. So from instructor as I, that's also valid SQL standard syntax. I don't for some reason, because I'm weird, but I think it looks messy, but that's just me. Now, if you're reading the book, if you have a print copy of the book, it teaches you to do something that we all do not like. And I don't know why. So I'll go through that. If you're reading the PDF that I posted, I've dropped this page. It's not there. If you're not reading it all, then you don't have to worry about this nuance. The book shows you this method on how to write a join. In particular, the from contains two tables, and the join condition is placed in a where. Do not do this. It's old-fashioned, it's inefficient, and it won't get credit. So forget you ever saw this. The textbook also talks about using. So when you have two tables that have the same column name, and you use that column as the join key, instead of specifying table 1 dot key equals table 2 dot key, you just specify using key. Great, we're not doing it in this class. In this class, every join must have an explicit join condition. So, some theory, some people teach us using Venn diagrams. If you want, it's not always clear what we're computing in the Venn diagram or the set intersection on, but basically what this is saying is there's a bunch of records in R, there's a bunch of records on S. We only keep the intersection where the keys match. The key values match in both relations. So sometimes I think I have too many slides covering the exact same thing, but I suppose it's good for a review. Here we have the same result again. Here I want to point out though that the cardinality of the relationship, meaning how many matches are on each side, doesn't matter. We see for one Smallberg, we have 2 courses. For one Eggert, we have 3 courses. That's okay. I can also have, if I had 2 DA Smallbergs, then I could have one of them go to 2 courses and the other Smallberg could go to 3 other courses. Who knows? So we could have 1 to 1, 1 to many, many to many, and many to 1. A inner equijoin does not give you a 1-to-1 relationship except under one circumstance. That's when you're joining on keys on 2 different tables, primary keys for uniqueness. So for the millionth time, we get back 2 Smallbergs, 3 Eggerts, and everybody else teaches 1 class. And there's no Smith again. So are there any questions on the inner join? Mm-hmm.
What is the difference between inner join and theta join?
Inner join and what?
And theta join?
An inner join is a kind of theta join. Everything we discuss in this lecture today, except natural join, is a theta join. So actually, that's a great question to get me to my next slide. These joins, these aren't all orthogonal. It's a non-equijoin, or it's a inner join, or it's a theta join. These are all, or they're not mutually exclusive. A join can be of multiple categories. So what we just learned is an inner join, but it's actually also an equijoin. It's the easiest version of an inner join. But there are a bunch of other ways we can characterize joins. First, based on how we handle rows that do not have a match in S. So in an inner join, what do? Toss them. There is another kind of join, an outer join, or we may keep them. Number 2, based on the operator using the join condition. In the example we saw so far, we only had one. We had a very simple join condition. It was just something equals something. But this can be very complicated, and we'll see those examples this lecture. If all the operators are equal, it's an equijoin. If there's only equal signs. Otherwise, it's a non-equijoin. So if I have any operator that is not an equal sign, I'm not saying not equal to, I'm saying if there's any operator that is not the equal sign, it is a non-equijoin. Number 3, based on whether or not we join a table with itself. If we join a table with itself, it's called a self-join. There is no name for a non-self join, as far as I know. Based on whether or not we explicitly state the columns using the join. Well, this is natural versus theta. And we know that a natural join's bad. Bad. Gosh, I'm getting delirious. Number 5, joins with no join condition or an incomplete join condition. So it's possible to write a straight up cross join, which is a Cartesian product. All tuples paired with all tuples in the other table. Now, sometimes you write a join and you're missing part of the join condition and you don't know it. This is also a cross join. You have a little cross join embedded in the rest of your query. And you will run into that. So we try to teach you this as best we can. You're all learning. You're not going to get it right all after this first 5 weeks. You may do very well, but when you go and do an internship, you're going to write a query wrong. We all do it. It's going to happen. You may crash the server and whatnot. It happens. But over time, you learn how to really tighten up these join conditions so that you can't get a cross join. I used to be very bad at this. I'd leave out a join condition, and then A 10,000 row query takes hours to produce a result. That's bad. So, join, so yes. What is what? Equijoin? An equijoin is a join where the join condition only contains equal signs. So column 1 equals column 2, and column 3 equals column 4, or column A equals column B. They're only equal signs. So the and and the or doesn't matter. It's the comparison operators that matter. So if they're all equal signs, it's an equijoin. That help? So equa versus non-equa, this is just yet another slide with a bunch of words on it. We've talked about if there's at least one operator that is not the equal sign, it's a non-equa join. So this also answers your question as well. Join, now we're going to move on to the next. So we're just kind of flying through some of these less interesting ones. We'll come back to non-equa though in a moment. Joining a table with itself, the self-join. These are often combined with other kinds of joins, in particular a non-equa join. So what are some examples where it makes sense to join a table with itself? Anyone know?
A table where an employee is marked to a manager, and there is so you might have to if you want to compute how many employees are under each manager, you might have to use that.
Yeah, you'd have to do a self join and then some kind of aggregation as well. Yeah, if you basically if you want to traverse an org chart, like from individual contributor all the way up to CEO. One thing we could do with a simple self join is compute who are all my skip levels? Who is my skip level? For each employee, find the skip level. So a skip level is your manager's manager. So compute this for each person. So you could do that with one self join. So an example of that is if I have some org chart here, this is the CEO. Now the table itself will contain the CEO's name and then a bunch of IDs in different rows for each of his subordinates or her subordinates. So this will be like the SVPs. Then I can do a self join to get who are the CEO's VPs. Basically, I take the CEO SVP relationship and join it to the SVP VP relationship essentially to hop from CEO down to VP. And I can figure out who all the VPs under the CEO are, or who are all the skip levels for each employee in the company, and so on and so forth. So this is called a tree. Network problems are big here, sometimes called graphs or social networks, or DAGs. So in computer science, a DAG is a special type of graph. It's directed, which I'll discuss in a minute, and it's acyclic. Directed means that when we traverse the graph, we can go from A, if there's an edge, A pointing to B, it may not be possible to go from B to A. We can only go A to B, it's a one-way street. Acyclic means there's no cycles in the graph, so we'll never get stuck in an infinite loop. So typically graphs are represented as vertices or nodes, which represent a thing or a person. And then we have lines or edges between them that denote a relationship. Then these edges may be directed or undirected. So in the directed case, this is like Twitter. A follows B, but it's not necessarily true that B follows A. Also, since you've graduated from college and you're a little older than high school, or maybe middle school is the cutoff. You've darn well learned, I know I have, that friendships are not reciprocal all the time. They are more like a directed graph or maybe a mixed graph. So more like directed. It's a sad world. We also have an undirected edge too. And this is more like Facebook, much to people's chagrin. So A is friends with B. This also implies that B is friends with A. This means A may want to see B's food pictures, but B does not necessarily want to see A's cat pictures. But we force it on them anyway. Maybe, that's the problem with Facebook. I don't know. And then they added this thing where you can follow people. So it's kind of a mixed graph, and under the hood it is mixed. And you can traverse the graph either with undirected or directed edges, but who cares right now? So let's solve a problem here. Let's say I have this little table, and at Facebook, for example, this is how a friendship is stored, or Twitter even. We have a user ID and the friend user ID. This means that 1 considers 2 to be a friend, 1 considers 3 to be a friend, 3 considers 5 to be a friend, and so on and so forth. So we can draw this as a graph. 1 considers 2 to be a friend. So we can draw a little arch here. 1 considers 3 to be a friend. 3 considers 5 to be a friend. And 5 considers 2 to be a friend. Aw, it forms a heart. Friendship's magical. But then we gotta ruin it with 3 considers 1 a friend. So it's a heart with some kind of abnormality on it. Oh, and this is called R. So this clear? Cool. So what does it mean in a social network to find a friend of a friend? This is an image I stole off the internet. Otherwise I would have, just drawn something more interesting. Here I am, and I have 3 friends. 1, 2, and 3. 3 friends. Sad life. But if you can count your friends on one hand with at least one finger, you're not doing too bad. Then all the circled people here are friend of a friend. So this guy is friends of this one. This one's friends with this one, and this one's friends of this one. So basically, I have 6 folks. 6 friends of a friend of myself. This is a many-to-many relationship. We're now going to write a SQL query to find these friends of a friend. It's challenging, but it's fun, and I'm going to show you a beautiful way to do it. Everyone ready? All right. So this is a strategy you can use for basic joins. Once you start adding group bys and halvings and subqueries, you can't use this as much anymore. You can use some of it, but you can't use all of it. So we'll go through this step by step. The first thing I do when I'm writing a basic join is identify the tables that I'm going to pull from. So here, it's the same table. It's R and R. Make a joke about my initials, but I'm running dry. Anyway, R and R. So I have 2 tables that represent the same thing, 2 copies of the same table. Great. One's the from, one's the join. Second, I compute the Cartesian product, all pairs between that little table. So I get a lot of rows from that little table. And I'll show this on the next slide as well. Do I write here? Oh, there's one catch here though. Remember, in the Cartesian product, I cannot do R cross R. I need to rename. So one of the R's is going to become an L for left. So row sub L of R cross R. Now, if we look at this Cartesian product here, this stuff over here comes from, R, and the stuff to the left-hand side comes from L, which is R, remember. So that's how we segregated these 2 sets of columns. Now what do we do? Well, now we have to write our join condition. Which is here. Okay, now what do? We notice a few things. First of all, what should the join condition be? Let's start off simple. What should it be? Or let's try it. Not simple, but let's try it. What? Yeah.
Second column equal to third column.
Yeah, second column equals the third column. That's a great concise way to describe it. Or we can start with theta equals L.FUID, I'll simplify it, equals R.UID. So we'll start there. Now, we notice a few things here. I have a match here. I have a match here. I have a match here. And I have 2 matches here. Now, there's a problem with this join condition though. Let's look at this first result. This means 5 is a friend of 1. That sounds legit. This next one, 1 is a friend of 1. Does that tell us anything? Not really. So let's get rid of it. We're going to have to filter that out. Next, I have 2 is a friend of 3. That sounds legit. I have 2 is a friend of 3. That's also legit, but also poses a problem. And finally, 3 is a friend of 3, which is bad. So how do I now change this join condition to eliminate those weird cases? Now, what do those weird cases represent in a graph? A cycle. Friend of a friend, 1 being a friend of 1 is a cycle. So we want to get rid of those. So how can we change the join condition to take that into account? So the first part's right still. It's L.fuid equals R.uid, but it's just not complete. What else do we need?
And
User ID is not equal
Which user ID?
to, any user ID is not equal.
Yes, L.user ID does not equal R.friend user ID. Excellent. So here's our join condition. Now, we've written a join condition. We know we're doing an we know we're doing an inner join, not an equijoin. It's a non-equijoin. Now we can start writing some relational algebra to represent this case. I'm going to write this to be clear, though. 3 is a FOF of 3, bad, of 3, bad. And then we're going to rewrite this as follows. The first thing I'm going to do is I compute the Cartesian product. And then to apply, I apply a selection operator because that's the definition of a join. L.fuid equals R.uid and L.uid is not equal to R.fuid. Now, this is equivalent to, by definition of a theta join, renaming R to L, and then using the bow tie operator in a theta join. L.fuid equals R.uid, and L.uid does not equal to R.fuid, R, capital big R. Now I'm going to call this psi, or whatever this Greek letter is, to bookmark it for some future use here. To be complete here, we're going to write 1 is a FOF of 1, which is bad. This way when you're reviewing in your notes, you understand what we did. Great. Okay. Now, we're not done quite yet, though we're getting there. We now need to look at step. Does anybody need this slide still? Or we can move on? Okay. We're not done yet. Now we need to identify what the output's going to look like. What do I want the output to look like? Which columns do I want to output? Let's go with you. Just shout it out. Yeah.
user, friend, and friend of a friend.
Which user and which friend?
So L dot user, L dot friend, and R dot.
Do we really need those? We just want to know who is a FOF of who.
Okay.
So the first one's right. Now what's the other one?
R dot.
Great. That. So we know what we want. We want L dot user ID, and we want R dot friend user ID. But we probably don't want these names. Let's rename L.user.id to be user, and friend user ID, who is the FOF, to be FOF. Now, we're still not done yet, because if we run this query, we're going to get the following. We get user, FOF, 1, 5, 3, 2, 3, 2. And what's wrong here? We have duplicates. We'll call this star to bookmark it. So what do we do to get rid of the duplicates? We do what? But in the relational algebra, we group? Yes, we do distinct and SQL, but what do we do in the relational algebra? Pi. Yeah, I think some of you are forgetting the pi operator exists. So pi removes dupes after column extraction. So, our relational algebra expression is going to be L.uid. I'm still going to use shorthand here. Gets renamed. That's what the right arrow does. You know what? Let me use the full name. I'm not going to be lazy. L dot user ID, and we're going to rename it. That's what the right arrow does, user, comma, R dot friend user ID, right arrow fof, applied to the thing that we just computed on the previous page, which I'm just going to copy and paste. So we have this guy here, and let's do this one. Copy, paste. Or we can do this a different way. We're going to duplicate this and use this other nice notation here using the bow tie operator. So copy, paste. Oh, I did the same one. Damn. Okay, let's do the other one. The one with the, that's this one here. And there we have it. The most complicated expression we've written so far. Any questions on the relational algebra expression we just wrote? Yes.
Not specifically the relational algebra, but I was wondering, instead of us having to use a non-equijoin like we did, can we use a where statement to eradicate those entries where there's a cycle?
Yes, you can. So the question is, instead of using the non-equijoin, can we use an equijoin and then just use a where to filter out the rows that don't match? Yes, we can. It's a little bit less efficient, especially in a big data system. So database systems, which are expensive, except for MySQL and the open source ones, have an optimizer. The optimizer is probably going to take what he said, which is do an equijoin followed by a where clause and convert it into a non-equijoin, a non-equiself join. And they're both equivalent. In a big data system, though, which typically don't have as sophisticated of optimizers, you may get different performance. It's better to put all the filters in the on where it makes sense, so that so under the hood, a database system is not actually generating a Cartesian product. It's kind of doing a smart search. It looks at all the pairs of tuples, but it doesn't really do much with the ones that don't match. So we're not actually outputting them anywhere. But in a big data system, let's see, where was I going with this? So we don't actually compute the Cartesian product in a relational database system. We do something smart. But in a big data system where we don't have a sophisticated optimizer, we actually do compute the Cartesian product. And then if we apply the where clause, we have to generate the Cartesian product and then filter out. Whereas with the on clause, we tend to filter out as we go. Okay. So any other questions? Yeah.
Another one. It's more of an abstract question. I was wondering if we're working with data that is part of one relation.
Mm-hmm.
Are there scenarios where a self-join is absolutely necessary, or can we always have an alternative filtering query that can filter out the same data as self-join?
If you have a self-join?
Yeah, I mean, is there a way to avoid the self-join and just by using those ways of having in group by statements, we can come up with the same?
Yes, there's two things you can do. The self-join can actually be replaced by two other types of SQL queries. One's a window function. So a self-join, a self-non-equijoin, where you're only looking at like the past 5 rows or the past 5 days or whatever. That's called a window function. And you would use a self-non-equijoin to compute it, but a window function maybe has nicer syntax. The other is a recursive SQL query. So if I want to find a fof, I could do 2 self-joins, but my join predicate is going to become very complicated. So instead, what I could do is write a recursive SQL query that essentially automates the self-join process. So yes, you could write it a different way. We're just starting at basic principles here. So any other questions here? Okay. 5:35, I'm going a lot slower this hour for some reason. All right, so this slide just represents what we just talked about. This number 1 here is the psi. Number 2 here is the star. Here's the result we get. So instead, if we call the relation friends instead of R and L, Let's write the SQL query for this. Now note that there is no special syntax for the self-join. There is no self-join in SQL. It's just join, and you specify the from and the join correspondingly. So, using my strategy, let's go back actually and figure out, well, to save time, let's just do it here. The first thing we do is we identify the two tables, and those are going to be our from and our join. So we have from friends, join friends, L and R. I have to give it an alias because I have the same table name. Then step 3, because step 2 is the Cartesian product, I'm going to specify my join condition. So this is L dot friend user ID equals R dot user ID and L dot user ID does not equal R dot friend user ID. Now what's left is just a select statement. What do I want my output to look like? So this is step 4. Select distinct. Good. L dot user ID as user, R dot friend user ID as both. And that's it.
Question there? What's the difference between using distinct or grouping by? Because the result is exactly the same.
Well, what are you grouping by and why?
You can just for having distinct values.
Oh, for distinct? Oh, yes, you can do that. You can do select, leave out the distinct, and then group by L dot user ID, R dot friend user ID. Yes, you can do that. It's the same thing. Yeah. I thought you were referring to the self-join, which I don't know how you do that with group by. But yes, you're right. We can replace a distinct with a group by. There's mixed. Some people really don't like distinct, so they like group by. I'm not going to specify a preference.
If you use distinct, imagine that you want to summarize something.
Mm-hmm.
The distinct filter the values, or
The distinct applies across all 3 columns, so it's only going to keep distinct. Like here, I have 2 columns. It's going to have distinct doubles.
Okay.
So 1, 3, 1, 2, but not another 1, 3. It's distributed across all columns. What kind of join is this? It's a self-join. What else? It's an inner. And? Yeah, it is a theta join.
Non-equijoin.
And a non-equijoin. Great. Okay. Natural join, again, is in a class of its own. It can be of almost any type, but it's dangerous. So we're talking about natural versus theta here. Cross joins we'll cover very quickly because they're not very incredibly useful. A cross join is essentially a Cartesian product, but you also get a cross join if you don't properly specify your join condition. So you have a little mini cross join within your query execution. What is one case where you may, although we have better ways of doing it nowadays, want to use a cross join intentionally? What's an example of an application of it? So matching, roommate matching, dating. Now, next we're going to talk about inner versus outer joins. Outer joins are very important. With the inner join, all we do is we look for matches between 2 key columns. And if there's a match, we output the matching row, we concatenate them together, and write them to the output. If we cannot find a match, though, in S, or in the right-hand relation, we don't report that row in the output. Now, if we have a mismatch with an outer join, if we have a mismatch, sometimes we want to keep some of the data, and that's what we do with an outer join. I'm going to try to get through left. We'll take a little bit of a delayed break, try to get through left outer join, and then we'll take a break, which is what I did last time. So say I join 2 tables together as a left outer join. The result has 4 columns in it. 2 of them are only from the left side, and 2 of them are from the right side. if I join L and R together and I have a match on the join key, I have a fully formed row as a result. But if I have a record in L that does not have a match in R, I'm still going to keep the columns that are associated with L and fill them in, whatever those are. But I'm going to bookmark that I don't have a match in R. And the way that I bookmark that is by filling in null. So I'll show an example of this in a moment of where this makes sense. You're working with this bird scooter table in your homework, and bird has to charge a user. You know a couple things. You know that trip contains information about a trip, and this table could be decomposed into a trip start and a trip end table. Why we want to do this, I'm not going to say because it's a bonus problem on your homework. The black there is because I've blocked out what the schema is, what the data types are, because you need to figure that out. So that's what the black represents. So I have trip decomposed into two other tables. Okay, now I have trip starts, trip ends. Now I want to get a table containing the full trip information so that I can charge the user. We're going to note here that a left outer join starts with an inner join. I match this first row 1 to 1. I have a match. So I output 1, 7:45, 5:50 p.m. there. I do the same thing with a row of 2. I have only one match for a trip ID of 2, so I only output 1 row, and it's a full row, and so on and so forth. I do it for 3 and 4, and then I get to 5. Now, for some reason, 5 did not report an end time for the trip. Why that may be, again, that's for you to decide on your homework. But what does the result look like? It looks like this. I keep the data from the left table. So 5, user ID 2, started at 1 p.m. But then all of the columns that are from the right-hand side are going to be set to null because there's no match. So end time is null. These first 3 columns come from the left table. This last column comes from the right table. So there's no match in the right table. We mark it null. In an inner join, though, this row goes away. So we have no evidence that this trip ever happened. We cannot charge the user. This is really bad for Bird, and they're going to lose a lot of money, and you're probably going to be out of a job. It's a lot of money to lose. How do we write it as SQL? Well, again, we start with basic principles. What are the 2 tables that I want to join? Trip start and trip end. I specify a left join. Now, I can also write outer here. That's optional. But when I'm doing an outer join, I have to specify left, right, or full. But the word outer is optional, just like inner is. I give them names, L and R, just for my sanity. My join condition is just L.tripID equals R.tripID. Then I specify what my output looks like. There's a bunch of interesting things going on here. First is the trip ID. I need a trip ID in the output, it's up there. I choose the left-hand side trip ID. Why can I not choose R.tripID?
You use the 5th one.
It might be null. It's an outer join. So R.tripID may be null. This has to be L.tripID. And I'll rename it trip ID. Now, I also have time in both of these tables. So I have to give an alias. L.time is going to be the start time because L is the start time, trip start table, and R.time is the end. I'm going to call it end time because R is the trip end table. Yeah.
You said if there's no match, it just puts null.
Yes.
But if the schema doesn't allow null values, does it overwrite the?
If you do a left join and we're talking about the output here. So if I were to write this into a schema where I specify not null for one of the columns, I'd have a problem. But I won't have a problem in the output when I output the join because I don't specify a schema for the output. It's just a result set. What else was interesting here? If we do not name clashes outer, great, we got it all. We don't really cover typically the outer joins in relational algebra, but you can see that here we have the little bug, the scary little bug. The antenna of the bug point to the direction of the outer join. I think it looks like a creepy looking bug. So here the antenna are on the left, this means it's a left outer join. A right outer join is the other side. So we talked about left outer join, now we're gonna quickly talk about the other kinds of outer joins that aren't as useful as a left outer join, but they may come in useful from time to time. First is a right outer join. A right outer join is basically the opposite of a left outer join, and it can be represented as L, right antenna, R, which by theorem is equal to R, left outer join, L. I don't know if it depends on which hand you use to write as to which type of outer join you prefer to use. Most people use a left outer join. I think in my 8 years of teaching a similar class, I've only had one student use a right outer join where I expected a left outer join. It's not wrong, I didn't take off points, it was just a little interesting to see. So that's the right outer join. It works almost exactly the same as the left outer join. We also have the full outer join. The full outer join combines an inner join, a left join, and a right join, all together in one. These are extremely rare and not incredibly useful. It's actually not even implemented in MySQL. But it is a part of the standard, so I'll teach you anyway. It's just you're not going to be able to write any code with it. Suppose the computer science department wants to do a course audit to plan for next year. So we have instructors. Not every instructor teaches a class each quarter. And we also have classes, and not every class has an instructor associated with it. How do we find who's not teaching and which classes are not being taught? Maybe we need this information to be able to determine which classes we can delete for next year if we don't have anybody to teach them. So here's a little table that I have. Again, I have instructor that has an ID and an instructor name. It also has a teachers table that contains a bunch of course names, the faculty ID that teaches the course, and sometimes null if nobody teaches the course. So 112 has not been offered for a while, and 1 is only offered once every couple of years or so. So what would I do now to create this audit? I want to get something that looks like the following. I have all the professors listed and all the course names listed. Some of the course names have null under instructor name. Some of the course names have null next to the instructor name. Here we see that ComSci 1 and 112 are not taught, don't have a teacher, don't have an instructor, and we see that Knockenberg and Nowatzki are not teaching anything that quarter. How would I write the SQL for that? Well, it's just very similar to our other outer joins. It's just full join teaches. Select blah blah from instructor, full join teaches, on ID equals faculty ID. There is no name clash in the faculty IDs here, so I don't need to specify a table alias. So full join, this is not working in MySQL, unfortunately. All right, so are there any questions about outer joins? When we talked about the self join, one thing that I left out was that in the sigma operator, in the subscript of the sigma operator, we had a join condition. And what I forgot to mention was that is that join condition the on or the where? In theory, it doesn't matter, but in practice, it does matter. So for example, with an inner join, it's probably not going to matter too much. With an outer join, though, it does actually matter if it's a where versus an on. But we're not writing outer joins in relational algebra. I explained earlier the efficiency trade-offs when using where versus on with the Cartesian product-based join. So basically, in theory, it's a where or an on, essentially. One thing I want you to think about is, can you always treat the where and the on as interchangeable with an outer join? This is something very, very important. I don't want to give it away. I want you to think about what happens when you accidentally interchange the two in an outer join. To give you a little bit of a outline of what the correct answer is here, when you use the on with an outer join, you are invalidating some rows. So if you specify a condition in the where, you may never get to that filter because the rows that you're trying to filter may already be filtered out and invalidated in the on because they might be filled with nulls. So there's a hint. That's on one of the homework assignments as a bonus. Actually, I don't think it's a bonus. It's important to know. It's a common error. Non-equijoins. Why am I doing this example of playing cards? Because I was asked this in an interview, believe it or not. I was asked to generate all poker hands using SQL, and I didn't know how to do it, but now I do. So say we have this little table that contains a card ID, the suit of the card, and the denomination or the value of the card. And if you're not familiar with a deck of cards, 2 is less than 3 is less than 10 is less than Jack, Queen, King, Ace, and we've imparted a particular order on the suits here. And on Postgres, you can actually put the suit, the little suit symbol in the column. We want to find all combinations of cards. Now remember, there's a difference between the word combinations and permutations. With a permutation, the order matters. So 2, heart, ace is not the same as ace of spades, 2 of hearts. These are not the same in a permutation. But they are the same in a combination. Now, we get duplicates if we're going to find all combinations, and I select both of these, I get duplicates. So how do I find all combinations of cards such that I don't have duplicates in the combination? Well, I do a cross join because that's always what I start with a join, and there it is. And then I do a restriction. I filter rows according to some join condition. Now the join condition is this: I want to eliminate half of the pairs of cards because we're looking at combinations, not permutations. So I want to impart an order on the cards. First, I want to select cards where the left card's value is less than the right card's value. But that's not it. If the 2 cards have the same value, then what? If I forget this next part of the join condition, I end up getting a really weird answer. This will work for cards where the denomination is different, but when the denomination is the same, I'm going to get all permutations of cards. So I also have to add in this or here. If the value of the 2 cards is equal, then I have to order by suit. The left-hand card must have the lower suit compared to the right-hand card. This perfectly eliminates basically half of the combinations of, or half the permutations of cards and gives me the combinations of cards that I need. This is essentially one example of a non-equijoin, a really nuanced example. And here's the relational algebra expression you would use here. But note that this one's tricky. So are there any questions about this non-equijoin? Aside from why on earth would we ever write this kind of query with this use case? All right. How do we write it in SQL? Well, now we have name clashes abound. So I have to use aliases everywhere. So I specify my from and my join. This is also a self join. And then I specify my join condition just like I did in relational algebra. This time I want all 4 columns, so I just select all 4 columns. I could probably even dump this example once we've talked about non-equijoins and the self-join. It's also a non-equi self-join, just like the graph traversal. So there's a lot of different kinds of joins you can write. There's also other ones we didn't talk about that we might get to next time, which are the semi-join and anti-join. But there's 4 main types that you use over and over again. And if you nail how to write these 4 types, you should be able to pass almost any interview. The inner join, mostly the inner equijoin. The outer join, which is usually a left outer join. The self join, and non-equijoins that are mixed with other kinds of joins. I'm not a big fan of teaching this through Venn diagrams because it's not really clear what the Venn diagram represents. It's supposed to represent sets of tuples. I don't think it's very clear, but some people like this. There's a handout that you can use. On the final exam, I'm probably not going to allow entirely open notes because of some things that happened last year. But what I might do is let you use a cheat sheet or a 5-pager or something like that. And this might be something you might want to put on it. For exams and homework, first I can get rid of this slide because it's just a repeat. I try not to have too many rules because there's a variety of styles and ways. For example, somebody just taught me, it's weird that you can do this in SQL, but it makes sense because it's consistent. I'll write it here. You can do this. Select foo A. This is not very readable. This is select foo as A, but you can do it. And that's fine. I can figure out what you're doing. But there's a lot of these weird things that you can do. And these are the ones that I'm mainly going to emphasize that you not do. I've already specified some in homework 1. For example, don't use order by 1 or order by 1, 2 or group by 1, 3. I don't know what 1, 3 is. The schema can change, and I don't know what those columns represent. Other things like using where instead of having with the subquery thing, that I specified not to do. So I tell you certain things not to do. Other things though, if it becomes an issue, maybe next year I'll be more strict about it. But something like this is minor. I can still figure out what you're doing. So the as is basically optional in both the select and the from and join. Anyway, let's delete this so it's not confusing. Never use natural join in SQL. Do not use using to do an equijoin. Don't use the select from BS where you use from multiple tables. Don't use any join method that doesn't explicitly list out the join condition. Don't use outer join for everything. One thing, sometimes people think they're clever and they'll write a query that uses full outer join everywhere and then just filter so that it looks like a left join or it looks like an inner join. Or they use a left outer join everywhere and they filter it down so it looks like an inner join. No, you need to use the right join type because we're learning in this class. What you do in your career, I don't care. But do not use outer join for everything. So that's just a repeat. All of these will be on the exam. You'll have the bitchy instructions of don't do this, don't do that. Anyway. Now we're going to talk about nested queries and subqueries, which is the one last major concept of how to construct a query. So a subquery means you can query a query, or query the results of a query, basically, by nesting them under other queries. This is sometimes unsophisticatedly called a select within a select. And I'm going to regret this, but it's a history lesson. Having has not always appeared in the SQL standard. Before, when we used having, we'd have to use a subquery. So here's a little example, find all majors, math, soc, whatever, that have an average GPA less than 3.95. Before having existed, we had to write this in a subquery. First, we would compute the major and the average GPA for each major. And then, to filter on that aggregate, we would do that outside of a subquery. Now, because I've already materialized the average as an alias called average, I can now use it outside of that subquery. And now I can use where, because it is no longer an aggregation function. So that's initially one of the uses of subqueries. Do not use a subquery. Here's another rule. To get around using having. All right. So sometimes there's a couple of different kinds of subqueries. One is called a derived table subquery. Sometimes we want to use the result of a query as input to another query. We're allowed to use a subquery in a select, which is mainly what we're going to talk about. And in some advanced cases, we can use it in insert, update, and delete. Now, one case that I mentioned earlier is what do we do if we don't know what the max on the exam was, but we know that we want to increase everybody's score by that delta? How do we do that? We can do that in a subquery using within set. So we compute what the delta is and then add that delta to every person's score. That may be a hint of something. Innermost subqueries are always executed first. So I don't want to be US-centric here, but some of you have probably heard of PEMDAS. Please excuse my dear Aunt Sally. The P stands for parentheses. The parentheses are always executed first. The innermost subquery is always executed first. If I have subquery within subquery A, within subquery B, within subquery C. Subquery A is executed first, followed by subquery B, followed by subquery C, followed by the outer query. So there's a couple of use cases of subqueries here. The two main ones are 1 and 2. We'll talk about the rest next time probably. One is I can construct derived tables that chain together different steps within a SQL query. The second is I can compute a constant. That's called a scalar subquery that I can use in a filter or I can use to update people's scores like I mentioned earlier. So I have this midterm scores table again. We're probably all sick of seeing it. And we're going to do a couple of weird things with this table. The first thing that we're going to do is we're going to separate grad students and undergraduate students into two different curves, two different distributions. Each distribution gets a z-score. So each undergrad is going to get a z-score. Each grad student is going to get a z-score. But it's on two different distributions. I need to compute mu and I need to compute sigma. How do I compute the z-score associated with each student depending on their career? First, if you're overwhelmed, just relax, because I get overwhelmed as well. And you just have to remember, what are you calculating? I have x. X is the midterm score. I need mu and sigma. These are both the result of an aggregation function. So I have to compute those first. So what do? I can compute those in a subquery. So I get a nice little table here that gives me career, mean, and SD. And it's sad that I have these memorized. 76, 67, 4, and 10. Now I have to do something with this table. I need to somehow get this table into my main table containing all the midterm scores so that I can compute the z-score. So what better way to do that than with a join? So I join, and once I join with the original scores, I get back a bigger table. This table is going to contain UID, last, first, MI. It's going to take career from one side. Let's call it the score side. It's going to contain the midterm score, mean, and SD for every student. Every student is going to have a mean and SD based on whatever their career is. Now, using all of this information, all the data that I need is now in a row. Now all I need to do is take the midterm, subtract the mean, and divide by the SD column, and I get a z-score. So by using the sub query here, I can get a nice aggregation to compute these z-scores by career. Now, there's one other thing I need to show you here, and that is this. This subquery here is called a derived table. Every derived table must have a name. That is literally the error message you get if you don't do that. Now, there's no conflicts, there's no name clashes here, so I don't actually use the name in the select statement, but there are many times where I do have to use it. And so I refer to that result of that subquery as aggregated. So I could replace mean with aggregated.mean and SD with aggregated.SD. If you do not put that aggregated there, you will get an error. Now in Postgres, I don't know if it's the same in MySQL. You can shut the database up by just naming that derived table underscore. Kind of like in Python, you want to get rid of something, you just name it underscore. And that basically handles the derived table and tells the database, I don't need a name for this, but to shut you up, I'm going to give it a name called underscore. Are there any questions so far on what this does? A derived table. So one thing you might want to do is you may want to automatically just do midterm, because sometimes I forget and get flustered, and then I do average midterm like this, divided by std dev midterm. First of all, this doesn't work because you're going to get an error. How do you know this is going to give you an error though? Because you're using a aggregation function, you have to follow the rule that everything that appears in the select must be in an aggregation function or appear in a group by. Now this outer query has no group by. Midterm appears in std.dev and in average, but it also appears by itself. I cannot do that. If I wanted to be clever, I could put that second midterm as floating there in another aggregation function and it would probably work. But because of that reason, just remember that reason. If you have an aggregation function, everything in the select must be in that in a function or in the group by. Then you'll understand why this doesn't work. Sometimes I forget myself, and if I just remember that rule and that error that I'm going to get, it's an easy way to remember not to do it. What you can do is something like this: average midterm plus 2. That's perfectly fine. Everything in, well, that's all that's in the select. All columns that are in the select are in an aggregation function or in a group by. The +2 is not a column, it's just a number. It's just a scalar. So something silly like that I can actually do. Anyway. If there's no questions about this, let's move on. So this is the result that we would get. The z-scores don't follow the same distribution, again, because it's different for grad and undergrad. But next type of subquery is a scalar well, before we get there, you can write a derived table subquery either in the from or in the join. They operate exactly the same. They also both have to have derived table aliases. Now, a scalar subquery is a subquery that returns exactly one value. We saw an example of this last time. So remember I asked you to find what is the most expensive app in this apps data. And we use order by to find it. Well, another way we could do it is we could use a subquery. Select app name, comma, price from apps, where price equals, then start a new subquery, select max price from apps. So that's a scalar subquery, an example of one. Let's say I'm no longer going to segregate or group undergrads and grads. I have to do it this way or the example gets too complicated. We want to identify students that scored at least half a standard deviation above the mean. How do we do that? First, I have to figure out what half a standard deviation above the mean means. No pun intended. So I do that in a subquery. This computes mu plus half of sigma. It's just a straight up global aggregate. Select average midterm plus 0.5 times standard deviation of midterm from midterm scores. And I'm going to compare against that value. I'm going to compare midterm greater than that value. So this whole thing returns one value, a scalar. So now I select a bunch of stuff from midterm scores where the midterm is greater than some score that defines the cutoff of half a standard deviation above the mean. Any questions so far? So second kind of subquery. This is also the type of subquery you would write to increase scores if you don't know what the max score on the exam was. Then you get this. This should say null, null. But these two fine people or signs, bears, are above half a standard deviation above the mean. For grad student, or no, it's for the whole class, disregard. Now, this does not work. Some people might be tempted to do this, and I've done this myself. You have to put the aggregation in a scalar subquery. We don't know what average midterm is. We don't know what standard deviation of midterm is. We haven't computed those yet. And more importantly, aggregate functions do not belong in where. So that's a where versus having issue also. Multiple point deductions for different reasons. Now, there was one other subquery that you really shouldn't write. Sometimes they come in useful, but for the most part, they're dangerous. This is a case where we're going to go back to looking at undergrads and grads again separately. Sorry. Now I want to compute which undergrad students scored above half a standard deviation above the undergrad mean, and which grad students scored above half a standard deviation above the graduate mean. How do I do that? Well, you might think that I could just write a scalar subquery like this. And I'm kind of doing a join here. I'm looking at each row and which career that row corresponds to, and figuring out what the average is for that career and what the standard deviation for that career is. This is kind of like a join. That's what this where is doing. But there's a problem. The problem is that m1.career inside the subquery is using the same alias outside the subquery. What this does, what the optimizer is going to do now, is for every single row, it's going to recompute that subquery. It's going to recompute, that subquery runs across all rows. But now I'm going to do that for every single row. So I basically get n1 times n2 complexity, quadratic complexity. If n1 is the size of, well, actually it's n squared because it's the same table. So they have the same number of rows. So you basically get n squared complexity here, which is extremely slow. There are cases where you want to use a correlated subquery. We might talk about it, but in general, this is bad. Instead, what should I do? I'm testing if you're still awake because it's written on the slide. Use a join instead. And the join is exactly the same kind of join that we did earlier. Except instead of computing the average like we did before, we're just computing the upper limit, folks. So what we could do is we could replace it with this join. So select career, average plus 0.5 times standard deviation as upper limit. Before, I think we just used an average there. From midterm scores, grouped by career. Now, this is a derived table now, not a scalar subquery, so I have to have a derived table alias there called limits. I'm going to join to midterm scores, which does the same thing as we did before. Now I'm going to have an upper limit in addition to everything else for each student, but the upper limit is going to correspond only to the career, so undergrad or grad. I'm going to join the two, and then I'm going to finally do a filter, where scores.midterm is greater than upper limit. I could also put that where in the on as well here. It's an inner join. So this is very similar to the example we just did about 10 minutes ago or so. So any questions? This is a common type of problem that I've asked before. Identify what is wrong with this query or what is wrong with this subquery. I get some interesting answers, and usually it's a correlated subquery. And I enjoy this one because some of the answer choices make no sense and people select it. That's always fun to see. So the problem is usually that it's a correlated subquery. So you select that answer choice. And then how do you fix it? Convert it to a join. This is a very common thing that you could potentially have to do. Okay. So this is what our table is going to look like. And the upper limit is different for Josie because she's a grad student, and the upper limit for Joe is different because he's an undergrad. The grad students did a bit better on the exam. So apparently, there's this little manual that teaches you how to use the gradebook. And Josie is apparently a doctoral student who has advanced to candidacy in mathematics. And Joe was apparently a undergraduate junior in econ, in case anybody cared. But I thought that was cute. Now, we've seen how subqueries can be rewritten as joins, and some joins can be rewritten as subqueries. When do we use which one? Some things to keep in mind. Do we really need a subquery? When I'm grading, this is really an art. Some people write subqueries for really silly things, like to dedupe. They'll write a really long query in a subquery, and then they'll say, select distinct from this big subquery. Why didn't you just write the select distinct inside? The best was on the final last year. I had one person. I thought they were trolling me because he was that kind of person, who did this. Actually, I'll write it on the iPad. Let's be inclusive. So he wrote select star. He did this. Select star from, and then here was his actual query. He did a couple other things, like he used where instead of having. This poor guy, he had a beautiful subquery, but got no credit on the problem because he made every single little mistake that could possibly be made. I emailed him about it afterwards. I said, dude. But the rest of the exam was fine. But I was just looking at this. Oh, goodness. You know, you're nervous. Things happen. So do we really need a subquery? Can we use a join instead? That's one thing that you may want to consider. Subqueries can usually be rewritten as joins, especially correlated ones. And how will the nested subquery affect performance? So if you ask people which one's more performant, sometimes you're going to hear people say that joins are more performant than subqueries. This is kind of lore that's been passed down from generation to generation. And it's not true. It depends on the optimizer. Actually, in a big data system, subqueries are extremely efficient because you can farm out these subqueries at different machines and you get increased parallelism. It really depends on what the database is doing in order to determine which one's more efficient. So we're not going to really worry about that. If you do, I don't know if I've mentioned this earlier, if on the homework you do something really complex and we can't understand it, in the past we've taken points off because we don't know what you're doing if it's not documented. So if you're an advanced student, something I'm doing differently this year is if you document what you're doing and why, and you can even give a profile about why you think it's faster, then we'll probably give you the points. I don't want to punish people because they're more advanced. My focus is on readability and simplicity, but if you are more advanced and you're going for efficiency, just let us know what you're doing because we don't have a lot of time to grade these things. So there's really no one-size-fits-all approach for performance. On an exam or homework, again, this is an art. Sometimes subqueries are unavoidable, so use them. But if you're using a subquery for something that just really is obvious that you don't need it, that's probably a problem with us. Sometimes I see what they're doing. I see why they use a subquery. That's fine, even if you can do it with a join. But like I said, it's kind of an art. So just try to not use them unless they're really necessary. Okay. Wow, as usual, we're ahead. I thought we were actually a little bit behind and we caught up. So, let's see. We may just end early because I don't want to get too ahead of the other class. There's one aspect of, we go till 7, so wow. I'll go slower with this then, I guess. There's one aspect of data management that I want to talk about here, and the rest we'll do next time. That's mainly the coalesce function because it's used frequently with the outer joins. So there's a few things that we haven't talked about yet: handling null values, how to change data types, and conditional statements. For handling null values, there's only a couple things to remember. So if you need a cheat sheet, you could just put this on it. I forget these myself, but if you do arithmetic with nulls, you get back null. So 3 plus null is null. If you do an aggregation though, so 3 plus 2 plus null is not the same thing as a sum of a column containing a 3, a 2, and a null. So if you do a sum or any aggregation involving nulls, the aggregation function ignores the nulls. So an average of 3, 3, and null is 3. It ignores the nulls. It's not like R. Count, though, counts non-null values. So if everything in the column is null, the count is 0. It's not null. If I have a mix of values and nulls, it only counts the non-null values. The rest, is there. It is a little nuanced, but if you need it, it's there. Coalesce. Coalesce is a good way to work with nulls. And it allows you to do 3 things. Pick a non-null value from a set of columns, substitute a default value when a null is present, and also deals with some of the nuances of arithmetic. So in particular, with the bird scooter example, we may have a case where a trip doesn't end, and we still need to charge the user. If we have a null end time, we're going to end up charging the user null, which is not good. So instead what we want to do is charge them a default rate. So if somebody stole the scooter or something else bad happened that was the user's fault, we're just going to charge them a flat rate of $500. So I select user ID, trip ID, and then coalesce. The coalesce function returns the first non-null value passed to it. So 1 plus 0.15 times end time minus start time, assuming that's in minutes. If the end time is null, end time minus start time becomes null. 1 plus 0.15 times the duration becomes null. So instead of returning null, we return 500. The first non-null value in the coalesce is returned. So we charge the user $500 if there's no end time to the ride. Any questions? Okay. We can also use this to pick a non-null value from a series of columns. Let's say I have a table. It contains some staff information, It contains a home phone number, a cell phone number, a landline number, a fax number, a beeper number, all kinds of different phone numbers. But in the staff directory, all we care about is that there's some phone number there. We don't care what it is, it's just some kind of phone number. So we can use the coalesce function to pick the first non-null column to return in the result. Now note that coalesce home phone does not equal coalesce cell phone home phone because it returns the first non-null value. It's going to return a different result. So if I use coalesce home phone cell phone, I'm going to get back the first non-null number, and I call it phone number. So Sarah Smiles doesn't like to be contacted on the phone by anybody, so all of her phone numbers are null, and so she's null in the directory. Now if I replace that coalesce with cell phone home phone, let's see what would happen. The phone number would actually be the same in this case. Yes, but in general, it's not true that they're equal. Now, we can also use coalesce for nuances of arithmetic, in particular, dividing by 0. So back in the days when Twitter research was hot, we would often look at the ratio of followers to following, and the more followers a user had compared to the number of this should be, well, you could do it either way. The more followers a user has, the more influential they are, depending on how few people they follow themselves. So for example, I don't know, J-Lo has I don't know how many millions of followers, but it's probably not following many people. She's probably a celebrity or pretty, influential or something. So some people though will have 0 followers in this ratio. So this is somebody that just, doesn't really write anything on Twitter maybe. So their ratio is gonna be null because we've divided by 0, which is always a bad thing. What we could do instead is we could put the ratio in the coalesce. So if following divided by followers is null, replace it with 0.0. Coalesce is the SQL standard way of replacing a null value with something else. There is a function called if null that is MySQL specific. Do not use it. This appeared over and over on the final last year, which was suspicious in itself because I didn't teach it. So coalesce is how you want to pick a non-null value, not if null. If null only works in MySQL. Only MySQL. All right. First of all, the date's wrong. It should say the 18th. I won't go over part 1. That should take you 10 minutes. Let's see, what do I want to say about... So on part 2, I'm basically giving you, the reason why it's so wordy is because I'm giving you very specific hints as to what data type to use. It's not to trick you. It's just that, there's many different data types we could use. You need to use a specific one, and I tell you which one to use. So you have some exercises, you have a bunch of bonus exercises. Right, so the bonus exercises, we've been asked to do this. I don't know if other people do this, but I know we're generally asked to do this. This is for people who may be more advanced and aren't challenged enough by some of the other stuff. So typically there's a lot of bonus on this assignment. I don't know if I'm gonna cap it at a certain amount or if I'm just gonna let it go infinitely over 100, probably not. But one question came up, like if I do like 20% on the rest of the homework and then get all the bonus right, can I still get 100? No, that's not gonna fly. So don't try to do that. But it's meant to kind of boost you up and maybe replace some points that you may lose along the way, or just give you a bonus overall. All right, so the SQL part. Is there anything I want to say here? Because this is kind of unprepared. Prepared remarks here. Remember that each row here represents a month worth of data. It's not a row per passenger. It's each row is a month worth of data. So you might see some strange wording like take the monthly average over a full year. That basically means take the average of the rows for each month over the year. So one row is January, February, March. You're taking the average over those rows and putting them and treating that as your average for the year. So it's a monthly average over a year. When I say extract a time series, I don't really mean anything. challenging about that. It's just basically just returning data that can be used to plot a time series. I almost thought about asking about that in a bonus, like, plot the time series, but you have other classes for that. It just means get the data so that you can plot the time series. There's a couple of things that people, so let's see, I want to try to be reasonable if people do things a different way. It just depends on how unreasonable the method is. One thing that came up is arrivals and departures. When you're asked to summarize a terminal, arrivals and departures, it means you have a row for that terminal's arrivals and a row for that terminal's departures. It doesn't mean you need to have a row for the terminal and then 2 columns representing the arrivals and departures. That's too difficult. That's called a pivot, and we'll talk about it week 5, but I don't expect you to do that. If you try to do it, it's really gonna depend on the method you use, if it seems reasonable or not. If it's very inefficient or very ugly, then we won't do it because we did teach an easier way for you to do it. So that's basically, if you're advanced and you do it correctly and it makes sense and it's readable, you'll probably get the credit. But if it's really just unwieldy, it's kind of an art to determine that, then it will probably lose points. So you should always start by doing some exploratory data analysis, and I'm trying to enforce that in this homework assignment. How many rows do you have? Do you have any missing data? What does the data look like? Because you may not always understand the context of the problem. This context is something that I am absolutely in love with, and this data I am infatuated with. So I can tell you exactly why there are some problems with this data, but I want you to figure it out as somebody who may not be as interested in it as I am. Let's see. All of the parts, except for the bonus maybe, in number 3, we kind of did something very similar in the exercise session last time. So none of these should be all that challenging, except maybe the wording. Now, some of the wording is intentionally vague because we need you to figure out the data intuition here. If something is just incomprehensible, I tend to write in long, flowy, run-on sentences. If something is incomprehensible, that's a different matter. Please do let me know if something just absolutely does not make sense to you. I need to work on that myself, wording things so that it's universally understood. But sometimes it is intentionally vague, so just know that. And this job is very vague. Let's see, what else can I say here? Are there any specific questions? Yeah.
2C.
2C?
Do we need a code or do we need an explanation?
Oh, yes. Yeah, this one's been problematic. Part A needs to be syntactically correct. If we run it, it needs to run. Somebody asked me, should I check that the queries run? Yes, that's why we give you access to the server. The queries need to run because we're going to run them. So if they don't run, you're going to lose points. So you need to write code for the SQL schema, the create table statement. It says that right there. For part B, drawing the schema diagram, you have to draw it. You can use software to do it, to create the box and everything, but do not use a tool that automatically generates the query diagram. That's not what we're getting at here. You should do it like we did in the lecture 1 slides. What was the other issue that came up here? Modifying your schema. This is a great question. Honestly, so there's 2 ways you could interpret this. One is taking the original create table statement you wrote and just changing one of the columns, or multiple columns if need be. The other way you could do it is you could use alter table. I wasn't expecting you to use alter table, but if you do it, that's not a bad thing, or do both. But really, you just need to change the schema. Let's see, and I'm trying to kill time as this sheet goes around. Any other questions? We'll see how long we can drag this out. Please hurry. If you want, just put your first name and your UID, or even initials in your UID. Any other questions on the homework? Mm-hmm.
So does the homework require what we learned today?
Require what?
What we learned today?
No. Homework 1 is last time and before. You'll have another homework given out this week that will cover this week. Someone else had a question over here. Yeah.
The having filters on the audio that we are grouping by, right? It's like first grouping by and then the having filters.
Yeah, group by always occurs before having. And you use having to filter on an aggregate function.
Okay, I have a question for the question number 3, part J.
3 part J.
Uh-huh.
Oh my gosh, there's a part J. There is no part J.
G, sorry,
G.
Yeah.
Okay.
There you ask for the total throughout, like the total throughout value, the sum,
Mhm.
with more than 1 million passengers over
Mhm.
the entire time. But the result that we are trying to give is terminal and by year. So
Yeah.
the equation is different. We can't use a having there, right?
Yeah, you can use a having.
Yeah?
Yeah.
But the having is gonna filter based on month. Because we're on year, sorry, not on month.
It depends on how you do your group by. So check your group by. The only purpose of the having there really is to eliminate terminals that have very low throughput. Some of these, and to test the concept. So I would just check your group by, and that might make more sense. Yeah.
For bonus questions, we have to like provide like an attempt or
Provide a what?
attempt,
Attempt?
like attempt to solve it or just put it
Oh, for the bonus, okay, so for the bonus is not graded as leniently as the other problems. It's typically all points or no points. So if you attempt it, if you make a very, very solid attempt and get very close, you may get all or most of the points. If you kind of just attempt it, but it doesn't really make sense, or it doesn't address the question, it's probably gonna be closer to 0 points on the bonus, because it's bonus. It's not graded as leniently as the other things. Yeah.
Question number 2, like the part just above exercise 8.
Number 2,
It's about the longitudes and latitudes.
yes.
Do we need to have like total 2 columns or per drop, like 1 column for 1 drop? How do I approach this?
Okay, which, number 2, exactly one user ID.
Just above exercise 8.
I do mention a GPS in here somewhere.
A pick up and drop off.
I don't see where you're referring to.
Part 4.
Pick up and drop off location. Okay. Hint here, we talked about spatial data types. So requirement 4 is a pickup and a drop off location. The hint here is that we're talking about a spatial data type we want here. A pickup location contains a latitude and a longitude, and a drop off location contains a latitude and a longitude. Uh-huh.
The above table, like the table for customer number 2, do we need to include all the information about time, like midnight and exact date, like the first of the month?
Which number is this?
Just the table customer, right above. The
Part 2 or part 1? Part 2?
Exercise 1, and you want to create a table for customer. And the second requirement is to include the time for the expiration date.
Oh, uh-huh. And what's your question on that? I see where you're talking about now.
Do we need to include all the information about the midnight and the first date of the month?
So this one I'm going to leave to you. We do not have a data type that can be used natively for an expiration date. So an expiration date is a month and a year. Quite frankly, I don't know how expiration dates are handled with credit cards. Which time zone it's based on? Is it based on midnight? Do you have a little bit of a grace period? I don't know. So I'm a little lenient here. Because of that, it's a little vague. So which data type is vague? So you could choose a vague one or you could choose a more precise one. I'd accept either. So the question was about, for the other lecturer who's listening in, the question was about the expiration date. How do we represent it? And how much information do we need to include in it? It's intentionally vague. I'll accept something either weak or something very precise for that one. But it needs to have a date, a month and a day at least. Okay, where's the sheet now? Okay, so what we might do is once we're done here, if it's still not done, somebody leave it in the back and just sign it. That might be a better way to handle it. Okay, so any other things I can answer on this? I mean, sometimes in the past I have gone through some of them, but I don't know exactly what you're having issues with. So feel free to just ask, and I'll help. Let's see if I can think of something to say on on some of these other ones. So a startup, having no more than 10,000 scooters, that's important. Saying things like it begins its life offline, that means something. Bird has at most 500,000 users for now. That tells you something.